This is Lab 4, Circuits and Capacitors. The purpose of this lab is to use the concepts of conservation of energy and charge to predict the behavior of circuits containing resistors. We will observe the circuits that have resistors both in series and in parallel. We will use multimeters to measure the actual values of conventional current and potential difference in the circuits. The fundamental physical principles that I will use in this lab are conservation of energy, conservation of charge, the loop rule, the node rule, and Ohm's rule. For the first part of the experiment, I set up a circuit with 2 batteries and 2 ammeters. I then calculated a predicted value for I, which was the same as the actual value. For the next part of the experiment, I replaced one of the ammeters with a voltmeter. In this case, the ammeter read 0 amps. This is because the circuit is closed and the voltmeter has such high resistance that the ammeter is not able to measure a current. The voltmeter read 3 volts because there's no potential difference for the resistors and you only need to consider the batteries, which have a total potential difference of 3 volts. For the next part, I had to find the total potential difference in the circuit shown to the left. To do this, I found the potential differences between each point and summed them together to get 0. Using the data found before, I created a graph of the potential versus circuit position. For the next part of the lab, I had to answer questions and do calculations. The first question was, when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? It doesn't change because the voltmeter has high resistance, so a negligible current flows through it. Therefore, the change in the ammeter reading is negligible. For the next part, it asks, when you connect the voltmeter across an 100 ohm resistor again, note the ammeter readings. In this case, I got 0.02 amps. Next, I was asked to replace the voltmeter with an ammeter in parallel with a 100 ohm resistor. It asked what happened to the current through the other ammeter and why. The current became 0.06 amps. Since the ammeter is in parallel with the resistor, the current is then divided, resulting in a smaller current. The ammeter does not have a strong resistance, unlike the voltmeters, so current does flow through it. For the next part, I had to calculate the resistance at several different instances. I found R of the 47 ohm resistor to be 47.95, R of the 100 ohm resistor to be 102.05, R of the wire to be 0, and R of the ammeter to also be 0. For the next part of the lab, I observed an RC circuit. My observations were as follows. For the battery and the capacitor connected with a 10 ohm bulb in series, the light starts bright and then dims as the capacitor charges and the current decreases. Eventually, the light goes out when the capacitor is fully charged and there is no current. For the capacitor and the 10 ohm bulb connected with series, the light is bright and then dims as the charge discharges, meaning that the capacitor is giving its charge to the light bulb. The current begins to decrease until the capacitor is completely discharged and the current is 0. The time for the capacitor to charge and discharge are as follows. For the 10 ohm bulb, the charge was 10.65 seconds and the discharge was 10.71 seconds. For the 20 ohm bulb, the charge was 18.30 seconds and the discharge was 18.54 seconds. In this part of the lab, I utilized the assumption that electric field in connecting wires is negligible and the formulas associated with energy conservation as shown to the right. In order to find the time constant RC, I plotted ln of delta V over delta V naught versus time. I first found my predicted value of RC by multiplying 30 ohms by 0.2 and got 6. I then used the method shown before and the graph shown to the left to find the actual RC to be 6 seconds. I had to answer the following questions about the lab. The first one was, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter has resistance, while the virtual ammeter has no resistance. This resistance causes there to be a potential difference from one end of the ammeter to the other. This would affect the overall potential differences in the circuit and the current. The second question I had to answer was, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. With no resistor, the capacitor would charge much more quickly than with the resistor present in the circuit. In the ideal model, the capacitor would reach a full charge the second it is attached to a battery. This would not happen in real life because the ideal model assumes negligible electric field and resistance in the wires and battery.